Hello and welcome back for another presentation in your California geography course. This time we're going to be talking about California's Great Basin, which really is an iconic space because if you think about it, it includes everything from beyond Mono Lake to the north down to Death Valley to the south. So it includes a tremendous biodiversity of plant and life and vegetation, and you probably just thought I said Death Valley, and yes, those things exist there too. So there's just a lot to be explored here, so I'm really excited to share this with you. So that being said, let's get going. All right, so in the beginning, where is the Great Basin? So here's a great map showing. So you can see the Great Basin takes almost all over Nevada, up into Oregon, Idaho, even into Utah. We're really focused mostly on what's going to be in California, okay? So that being said, the Great Basin is the largest area of contiguous endorheic watersheds. That means endorheic means that it has no way to escape to the ocean, so it ends in the lake itself. It spans nearly all of Nevada, much of Utah, portions of California, Idaho, Oregon, Wyoming, and parts of Baja California. It is noted for both its arid climate and the basin and range topography that varies from the North American low point at Badwater Basin and Death Valley to one of the highest points just 100 miles away at the summit at Mount Whitney. So let's see, Death Valley, Badwater Basin's negative 282 feet below sea level. So if you were standing at Badwater Basin and Badwater Basin were to somehow magically move towards the ocean, you'd be under the water by 282 feet. On the flip side, because from Badwater Basin to Mount Whitney, you're looking at 14,508 feet above sea level. So we're seeing not just one of the lowest, but the highest elevation within our region. So we'll start at the top in the northern part of the basin, which is considered the Mono and Ino County region. So the Ino Craters are a chain of volcanic vents, domes, and lava flows along the eastern Sierra that stretches about 25 miles in length. They're just north of the much larger Long Valley Caldera system, but they are associated. So the image on the right, you can see the lake that's here. That is Mono Lake itself. In fact, if you squint really tightly, you can see some of the ancient shorelines from when that was a much larger lake itself. Mono Lake, as we'll talk about later, it was part of a spillover theory, meaning that when this lake had filled at its maxima with water, it spilled over into other lakes, ending at its largest lake down south in what we call Lake Manly, which would later be known to us as Death Valley. So I mentioned that there's been some unique volcanic activity. We still see some active geologic and geothermal evidence there between fumaroles and hot springs. But the chain itself is characterized by both explosive and effusive eruptions, producing a variety of volcanic features. We've got a plethora of cinders and plug domes that are found within this area. In fact, all of these little circles on this map are all different craters or remnants of domes. So we have rhyolitic lava flows. The most prominent features are rhyolitic lava domes and flows, which are distinctive in their shapes compared to others. And then we have phreatic eruptions. These explosive eruptions occur when magma interacts with that groundwater, resulting in a steam explosion and creating these massive craters. An excellent example of a phreatic eruption would be what we see in Death Valley at Ubehebe Crater. It's this massive crater that essentially blew its top, exposing all of its underlying geology around it. And also the tectonic setting in this area of the Ino Craters are located in a region of extensional tectonics, meaning that the Earth is pulling itself apart, it's separating itself, so creating a very, very thin crust. So moving forward, we can look at Long Valley as mentioned. So the Long Valley caldera is a massive volcanic caldera located along the eastern Sierra. It formed about 760,000 years ago during a catastrophic eruption that released a vast amount of volcanic ash and pumice, creating what we now know as the Bishop Tuff. The eruption emptied the magma chamber beneath the area, causing the ground to collapse and to form a caldera. The caldera alone is about 20 miles in length, 11 miles wide, and is one of the largest calderas in the world. But what about Yellowstone? So Yellowstone, which is also what we consider a supervolcano, which is one of the largest volcanoes we have on the North American continent in that sense, believed to even be part of the straw that breaks the camel's back in the end of one of our last mass extinctions, by causing a global cooling by putting so much ash in the atmosphere. But anyway, That happened about the same time as this. In fact, there are deposits in the Mojave Desert where we find both Long Valley deposits and the Yellowstone deposits of ash. But big stuff. These are big volcanoes. So this is the boundary itself. So it's been between, here's Mono Lake to the north, Lake Crowley at the bottom. It's right in between the two, and Owens River cuts right through it. So what are some of the things that we can still see there? We need to acknowledge the geothermal activity. So fumaroles are vents in the Earth's surface that emit steam and volcanic gases. They form in areas of volcanic activity, often near active or recently active volcanoes. So when I think of fumaroles, I think of if you ever eat anything really spicy and you get that like indigestion and you kind of burp it up a little bit, that's what a fumarole is. It's essentially the Earth burping up this steam. It's just really hot, like very dangerously hot. So you're probably familiar with geysers. Geysers like Old Faithful, where you have essentially these pots of water that end up boiling until they reach their capacity and they blow it out, and it's all steam and vapor and boiling water that comes out. That's a geyser. It's liquid and steam. Fumaroles, on the other hand, are just steam. So it's just burping out the steam. All right, so let's see here what we have. Magma chambers. Oh, magma, molten rock, rises from deep within the Earth. These magma chambers are essentially radiating heat outward, and in that process, if there's underground water present, that water, depending on how hot that magma chamber is, will allow for boiling to occur, building up pressure, heat rises, and it heads towards the surface. So it says heat and pressure. As magma rises close to the surface, it heats surrounding rocks in the groundwater, and then that heated groundwater will turn into steam, and then we have what we consider a fracture formation. So the pressure from the steam and the magma will force its way through cracks and actually fracture and crack it apart, giving way for that steam to be released. So here's a photo of one of my favorite spots. This is up, it's Hot Creek, north of Bishop, closer to Convict Lake. So it says danger, scalding water. So this is a runoff stream, and it comes from snowmelt, so it can be very cold. However, you don't know where they are, but there are essentially spots underneath it that are excreting that really hot water. These are actually hot springs here. You can see that the mineral and algae buildup creates a very unique, it's like a blue color, really pretty. And then the fumaroles are kind of here in the foreground, and there's farther ones down. But it's crazy to me to see people go in there. They want to go in these hot springs, and they're unpredictable. I mean, these are not like a hot tub hot springs where maybe you're looking at like 90 to 100 degrees. Some of these can be 250 degrees and beyond, to the point that you'll poach yourself like an egg. So when signed not to go in, don't go in. It's for your safety. All right, so let's talk about Mono Lake. So Mono Lake is one of the oldest lakes in North America, estimated to be over 1 million years old, and it is a terminal lake, meaning that it has no outlet. It goes into the lake now, and it doesn't go anywhere. At some point, there was, much earlier on, it did allow for some spillover during the late Pleistocene, but generally it is a terminal lake. It's to its own, it's endorheic. Anyway, so since it has no outlet, water can only leave through evaporation. This process has led to a really high concentration of salts and minerals in the lake, making it an alkaline and saline lake. So it's like if you ever boiled water before you pour it out of the faucet, put it in the pot, put it on the stove, and you cook it, and then you forget about it, you come back and there's white powder left in the bottom. So pure water was, evaporating. It's that process of going from liquid to a vapor, and it's gone. But it cannot take the minerals behind. So it leaves minerals behind that cannot be evaporated. We call those evaporate minerals. And most familiar would be halite or salt. So this is kind of the brief history. So the ancient formation, the lake formed in a basin created by and as the result of tectonic activity millions of years ago, and has a very unique ecosystem. So over time, that lake developed a unique system adapting to its extreme conditions, which include the brine shrimp and alkali flies, which supported a diverse bird population. So brine shrimp, which is this photo here in the bottom, that's how you probably know them as. There's two here. I know them as sea monkeys. That was a big thing in the 60s and 70s and 80s and 90s, where you would order freeze-dried brine shrimp, put them in a little container, and then they would absorb the moisture and become little brine shrimp, sea monkeys. Anyway, they exist here at Mono Lake, and because of that, the birds, the California gull, and many other migratory birds make this area its home because of the plethora of food supply. Even some of the early indigenous people made it as well, because they would use the larvae from the alkali flies, which is little very irritating flies. They're very, very small. They would take the larva and make like a pancake out of it and cook it. So the human impact in the mid-20th century, Los Angeles began diverting water from the streams that fed into Mono Lake to meet Los Angeles' growing water needs. That's the Los Angeles Water Wars with the aqueduct. This led to a significant decline in the lake's water level and a threat to its overall ecosystem, because Mono Lake itself has an island in the middle, and that island's where a lot of the birds would nest. But the lake levels were so low that it created a land bridge, and predators such as coyotes could actually get to that island. So back in the 90s, there was a water restoration effort. The court order mandated that the water diversions be reduced, allowing the lake to recover. Mono Lake in the Crater Mono Basin is now a very high alkaline or soda lake, and they completely limited any way for the water to be removed. So now it is truly an endorheic lake. It will only take in fresh runoff, and it will fill the lake until we don't have any of that runoff. So Mono Lake is unique because of these. These are called Tuat Towers. So to begin, alkalinity, which is a measurement of it's a measure of how many bases are in a solution and how well that solution can be neutralized by acids. So alkalinity often is pulled in with salinity. And then it says here also that carbonate and bicarbonate are both bases, hence Mono Lake has very high content of dissolved inorganic carbon. So Mono Lake already has a very increased dissolved load of carbonate and bicarbonate solutions. So because of that, subsurface waters will enter the bottom of the lake through small freshwater springs. So all around the lake are these massive mountains, right? The Sierra is an example, and then so they collect snow. The snow will melt and turn into water, and then will feed into the soil, and it slowly pushes down, and it is absorbed, it infiltrates the surface, and it pushes down. And in doing so, as it pushes down, it causes other things to come up. So you end up creating this natural spring. Well, in the process of that spring going up, this water that's now being pushed down and now going around and getting thrusted up into the lake, because of the composition of the lake itself and the composition of the fresh water going in, you end up creating a depositional mineral compound. So it says subsurface waters enter the bottom of Mono Lake through very small springs. These high concentrations of dissolved calcium ions in these subsurface waters will cause a huge amount of calcite to precipitate around these springs. So these columns that exist can only exist when completely submerged under the lake. So these have been exposed. So at one point the lake was these are about 6 foot tall. So at one point the lake would have covered this completely. So as the water is going through, from the underground water is infiltrating into the lake, it starts to crystallize, and in doing so, that water continues to go up and up and up and crystallize, and it creates like a straw. And that's what these are. These Tuat Towers are these massive depositional features from a mineral composition compound, which is pretty cool. They're protected. Don't touch them, because the acids in your hands and your lotions and stuff will actually cause the tufa to dissolve, because it's a calcium carbonate. So it'd be just like when you're in your shower, and on the shower head there's little white minerals that build up, and you use your CLR, your calcium lime remover, or you can use vinegar, a vinegar based with water, or you can do other things. It causes it to fuzz up, it fizzles while it's breaking down the chemicals, and it's dissolving the calcium, and that's what happens in this lake. All right, so that's Mono. Now we're going to move down south to the next one, and we're going to talk about Owens Valley. All right, now if you've had a chance to check out some other videos, it's great. If not, definitely check out the ones on the Owens Valley and the Water Wars and William Mulholland. I've got a lot to say here, and I'm just going to keep it really, really slim here, because I know that you can find that content elsewhere. So overview, Owens Valley, tectonics, volcanoes, and earthquakes. Oh my, covers a little bit of everything. So it says here first, basin and range extensional forces. The valley is the product, again, of the basin and range extensional forces, which is essentially pulling the earth away from itself. It's thinning out, like grabbing a piece of putty and pulling it. But by pulling it, you're creating extensional tension, but it ends up making it thinner in the middle. Moving on here, it says this extension has caused the land to stretch and fracture, resulting in the formation of mountain ranges and valleys. So the Owens Valley itself is enveloped by mountain ranges. So if you're in here in the valley, to this side you've got the Sierra Nevada. Down at the bottom southern part you have the Coso Range, and then on the right you're going to have part of the Ino Mountains and White Mountain chain. So you're enveloped by these massive mountain ranges. The Sierra at over 14,000 feet in most spots. Even the White Mountains are over a little over 14,000. Most of them are in the 12. So you're enveloped by this greatness, right? And as the mountains are continuing to go up and pulling apart, the valley continues to sink down. Faulting. The Sierra Nevada Fault and the White Mountain Faults bound the valley, and their movement has shaped the landscape. In fact, the Lone Pine fault which runs through Lone Pine was the culprit for their large earthquake, and I'll talk about that later. So we know that for volcanics, the Long Valley is north of us, so it's north of this area. This is where it is up here. But we also now have Fossil Falls and the Coastal Range down to the south. So again, it's surrounded. It's got volcanoes, mountains all around, and then it also has sand dunes on the eastern and southern margin. There are a plethora of smaller volcanic eruptions that have occurred within the area, contributing to the formation of these volcanic cones. So we do see that there's a lot of these red cones, cinder cones that do exist. Like I mentioned, Fossil Falls, which is another great video. If you haven't checked it out, be sure to check it out. Beautiful, iconic landscapes that are the result of explosive volcanics on our surface. So you have all of that present, but we also are going to have erosion, sedimentation, and then we have the lake. So glacial activity. So during past glacial periods, these glaciers helped carve valleys and deposit glacial sediments around the surrounding areas, which ended up not just shaping the landscape, providing imperative nutrients for soil, for agriculture. They can actually grow quite a bit up there. Water's the problem, but the soil's pretty good. We have these words: fluvial, which is river formed, and aeolian, which is wind formed processes. Rivers and winds have eroded the mountains and deposited those sediments in the valley, creating massive alluvial fans and bajadas, and also sand dunes that we can find within the region. Now, during the Pleistocene, we had these chain of lakes. So during much wetter periods in California's past, the valley was filled with large lakes such as Lake Russell. So you have, again, these massive lakes starting all the way up at Mono, and they were so big that they spilled over into Owens Valley, filling Owens Lake, and then moving farther down until it terminated down in Death Valley. So evaporation, diversion. So as climate became drier through time, the lakes began to shrink, eventually disappearing. Human interventions, such as the diversion of water for Los Angeles, further contributed to the drying of the lake. But the reality is, Owens Lake would have been what it is now. It would have essentially dried out on its own. The rate of evaporation, or how fast water evaporates, exceeds the amount of precipitation that they receive per year. So it's not a balance. They're spending way more than they can receive, and so you end up at a deficit. So I've mentioned Mount Whitney earlier. So Mount Whitney's formation is primarily linked to the Sierra Nevada batholith. This massive intrusion, or big block of granitic rock, occurred during the Cretaceous period between 80 and 180 million years ago. It took a long time because it formed and then it cooled, and then it reformed and then it cooled, and it kept getting reheated. And every time it got reheated, it got a little bit stronger, until now the Sierra Nevada, which is really one massive piece of granite, is one of the hardest rocks in the world. The crystals are huge. The quartz and the feldspar crystals in some places are larger than a brick, so they're very large. So we have this word intrusion. Intrusion means like when someone's talking and someone like cuts you off. They're intruding on your conversation. Rock has the same ability, especially when it's in molten form. It's able to wiggle its way through the pre-existing rock and filling that gap. So it says here, magma intrusion. Molten rock or magma will rise deep from within the Earth's crust and solidified underground, forming these large granitic bodies. Over millions of years, tectonic forces uplifted the Sierra Nevada range, exposing the granite batholith of this massive block. During the Ice Age, glaciers carved the mountain's peaks and valleys further, shaping its very distinctive profile. So yes, you're welcome. This is a beautiful diagram I created here. So this is the surrounding rock, the brown, and then the gray is the Sierra Nevada. So not only was this big block starting to tilt up, it also lost a big chunk down here that kind of helped lift it up a little bit, so because it wasn't as heavy. So in doing so, you cause this block to go bloop, and it pops right up. This high point is these points up here. This is the Sierra Nevada from the eastern side. So if you're on the other side, you're in Yosemite. So looking here, that right there, that peak where my little arrow, you see the mouse? That peak is Mount Whitney. That's the highest point. I know, you're thinking, no, that's the highest point. No, it is based on our perspective. That's Lone Pine Peak, but it's because it's closer. This is much further away. So that's actually the highest point, Mount Whitney, which is the highest peak along this block. So, I should back up, sorry. So these rocks in front are called the Alabama Hills. So the Alabama Hills are a range of rocks and formation located along the eastern Sierra slope of the Sierra Nevada on the Owens Valley side. So they are geologically part of the Sierra, but they differ dramatically based on appearance, patterns, and erosion. So they are much smaller in crystal size, which means that they cooled faster. And they're not as tall, so they're more susceptible to weathering. One of the most striking features of the Alabama Hills is their rounded contours, which contrast the sharp ridges of the Sierra Nevada to the west. The difference in appearance is because the Alabama Hills are made up out of a different style of rock. A common rock type is weathered, is metamorphosed volcanic rock that is about 150 to 200 million years old. This rock found along the eastern edge is relatively soft and easily eroded, which is why the Alabama Hills have such rounded contours. So there is a blend of small, fine-grained granite and metamorphic rock that is being able to erode, and in doing so, it creates these archways. These archways, there's over 100 of them. This is one of the largest, but I love it because this archway is a perfect window, again, to Mount Whitney. The most common rock type in the Alabama Hills is called a biotite monzogranite, which means it's a gravel-sized granite that has biotite in it, which is about 82 to 85 million years old. This rock is much harder and more resilient than the older metamorphosed volcanic rock, and as a result, the biotite monzonite in the Alabama Hills often weathers into these potato-shaped boulders that then can, in some cases, turn into an arch. So granite formed deep beneath the surface, cooling very slowly, and deep, and it's retaining all that stress and tension and pressure. And now that it's exposed, it's able to release, it's able to let go. And in that process, it creates these very bulbous, potato-like features, very similar to that of Joshua Tree in Southern California. All right, Alabama Hills. Any fun facts? Tons. Alabama Hills. So the California was not physically involved in the Civil War, but they were definitely emotionally and financially. So you had the Alabama Hills, which was a reference to the USS Alabama, which was a naval ship, and then you had the USS Kearsarge, which was another town nearby. So you had both sides of the North and the South present in California, naming these large areas after them because California was funding essentially part of the Civil War by extracting gold in these areas. All right, Alabama Hills. Oh, what else is cool? You probably have seen it in movies. Over 400 movies, over 1,000 television commercials have been filmed within these rocks. Everything from Iron Man, Django Unchained, The Lone Ranger, classic B-Western films with John Wayne or Roy Rogers. I mean, a ton. Every Jeep commercial has been filmed out there. You've seen it. You have seen it. All right. Now we move into the Southern Basin, which includes mostly one of my favorite places, Death Valley National Park. All right. Southern Basin. Thanks for your patience. I got to break this video up a little bit. It starts sounding like a frog because I'm talking so fast. So to the right, classic. I love these type of maps. This is before it was a national park. It was a national monument, and it's kind of pinpointing some of the iconic things. So here you have, the Death Valley Junction, which takes you over into Nevada on this side, or you can go to Rhyolite over here to the north. You've got Scotty's Castle to the farthest north of the park in Ubehebe, and then you have the Devil's Racetrack. You have the lowest point down here at Badwater Basin. So it's kind of a kitschy, silly, fun map, but I don't know, it's very 1950s. I love it. Love it, because I just feel like it's a fun way to see everything. So if you've never been to Death Valley, I've got a ton of videos on it. I recommend checking them out. It's a great place to visit in the spring, in the fall, and winter. Unless it's raining. Don't visit when it's raining. But otherwise, summer, you can stay away. It gets too hot. So let's talk about this. So the Mojave Desert is a desert bordered to the west by the Sierra Nevada mountain range and the California montane chaparral and woodlands, and to the south and east by the Sonoran Desert. The Mojave Desert is bordered by the San Andreas Fault to the southwest and the Garlock Fault to the north. The mountains elevated along the length of the San Andreas Fault provide a clear border between the Mojave Desert and the coastal regions to the west. The Garlock Fault separates the Mojave Desert from the Sierra Nevada and Tehachapi Mountains, which provide a natural border to the Mojave Desert. So the Mojave Desert is huge. Death Valley is in the Mojave Desert, so it even gets even bigger. So this is just a small fraction when I mentioned Death Valley. There are very few surface rivers in the Mojave Desert. Even given the low precipitation level, two major rivers generally flow underground. The intermittent Mojave River, which begins in the San Bernardino Mountains and disappears underground in the Mojave Desert, and the Amargosa River, which flows partly underground through the Mojave Desert along a southward path. The Mannix, the Mojave, and Little Mojave lakes are all large but very shallow. Soda Lake is the principal saline basin of the Mojave Desert. And it is believed that parts of the Mojave may have one of the largest underground freshwater storage systems, a massive lake underwater, but it's in an area that we can't quite get into. But it's fascinating. I mean, even like going back to Death Valley, like you think Death Valley is a place of nothing, barren wasteland, but they have fish. They have the pupfish, which is a fish that thrives in that area in these little streams that are on the surface for a very short period of time, and they submerge underneath the soil, and then they continue to flow underneath the ground. So let's check out the climate of the Southern Basin. So Death Valley National Park is a hot desert climate in the Köppen climate classification, known as a BWH. They receive freezing temperatures as well as very strong winds, as well as precipitation such as rain and snow in the mountains. It doesn't get a lot of rain. It usually gets, maybe 2 inches of rain per year, and it's usually one big event. There is an annual average precipitation between 2 to 6 inches. The rate of evaporation is about 130 inches per year. So that means it only rains 2 inches. But if you had a pool that was 130 inches deep full of water, it would evaporate within a year. So the rate of evaporation is exponentially greater than that of the precipitation that is received. So down below I've got some information from Death Valley National Park from 1911 to 2020. All-time high, 134 degrees. Otherwise, the average temperature in Death Valley throughout the course of the year during summer, May to September, you're all triple digits, but during the winters, you're down into the 60s. It's not even uncommon to be even colder. So what do we have here? All-time low was 15 degrees. The average high is 92, the average low is 65, and on average about 2.2 inches of rain per year. That's not, so an inch is the thickness of my thumb. So you're looking at that much rain, that much. It's standing, but it's in a big area, so it is quite a bit. So what is some of the history here? So it has some ancient beginnings, the geology of Death Valley. Beginning in the Precambrian era, the oldest rock in the park is over 1.7 billion years old, and they're extremely metamorphosed, which means that it's been worked over and worked over due to pressure, heat and pressure. In the Paleozoic era, shallow seas covered the region, depositing layers of limestones and sandstones. Then as time progressed, we saw in the Mesozoic era tectonic forces beginning to uplift the region, and erosion began to shape the overall landscape. In the Cenozoic, the basin and range extensional forces stretched the Earth's crust, creating the distinctive mountain ranges and valleys that we can see today. So this can be seen in this very again, iconic classic diagram. You're welcome. So here we have Death Valley in the middle. Here's Panamint Range. Here's the Black Mountains. So these are faulting. So as we have these extensional forces, the valley is sinking, but the mountains are increasing around it. Death Valley is in the rain shadow of a rain shadow of a rain shadow, which means, water that's coming off of the Pacific Ocean has to get over, the San Gabriels, and it has to get over, or depending how far north is, the Sierra Nevada, then it has to go over the Amargosa, then it has to go over the Panamint. This air and moisture has to be able to, through orographic lifting, be pushed up, and then it drops down and pushed up, and every time it does that, it loses more and more moisture. So by the time it gets there, it's very, very, very dry. Volcanoes, yes. Volcanic eruptions such as those that formed Ubi-Hibi, which was that steam explosion, have also shaped the landscape. Wind and water continue to erode the mountains and deposit sediment in the valleys, and the ongoing movement of Earth's tectonic plates will continue to influence the region's overall geology. So like I said before, I got a ton of videos on Death Valley if you want to check them out. Some on Badwater Basin. I've got some on the Devil's Golf Course, Artist Palette. Like, there's so many incredible, iconic things to see. And Zabriskie Point. I know it's hard to see because it's in the background. That's one of my favorite spots, is Zabriskie Point. It's just a beautiful overlook. If you wouldn't even know it's there unless you drive to it and get out of your car, walk up the hill, and then look over it, and it's absolutely, absolutely stunning. So I've mentioned the spillover thing, so let's talk about it for a moment because I feel it's important to do. So Ice Age Lake. So during the Pleistocene, at the beginning of the Pleistocene, about 2 million years ago, melting glaciers fed a chain of lakes in the region, including a massive one in Death Valley known as Lake Manly. So Lake Manly was nearly 100 miles long, and in some places over 600 feet deep, covering much of the Death Valley floor itself. It began to dry up. So as the climate warmed and glaciers began retreating around 10,000 plus years ago, Lake Manly began to dry up, leaving behind salt pans and playas. So here's Mono. Mono dipped into adobe, spilled over by the White Mountains into the Owens Valley, then China, Searles, then it spilled over into Panamint, and then lastly filled up Lake Manly or Death Valley. Massive, massive area. The evaporating water left behind abundant minerals deposits like sodium salts and borax. So Death Valley was known for the 20 Mule Team borax. You probably have used borax, or you've seen the little box as a detergent. Borax, it's a white powder. When I was a kid, they used to have these soap dispensers, and they go dunk, dunk, little needle, and then the powder would come down, and it would just lather very well. Borax was the white gold of the desert. That's what was pulled out of these areas in the greater Mojave, because it was, there wasn't a lot of gold out there. And this is what they were able to mine out. They used the borax mules, like donkeys, mules, to carry this out and get it on the train tracks and ship it around. Borax is still mined in some of these areas. One of the big open pits is in the town of Boron, and they mine it out there. They use borax not just for soaps and detergents, but it's also used in fertilizers, and there's different grades of it that are also used to create the glass on your cell phones. Dynamic, big place, but again, dry, because it's in the rain shadow. This is the Great Basin. It's dry. It's enveloped not just by mountains, but we also learned that it also has deserts to the north and to the south. So very, very dry air to begin with. Limited precipitation, but incredible geologic past. I could tell you stories about how when we were in Owens Valley, we were invited to help excavate a rear, I think it was rear leg of a woolly mammoth. Mammoth area? Probably you've heard of Mammoth Mountain. Mammoth, with the little icon is the woolly mammoth. The town of Mammoth was not named after a mammoth. Now you know. Google out why. It was a mining company. That's what they were named after. But anyway, the Great Basin, iconic. Mono Lake all the way down to the Greater Mojave. I hope this was helpful. Don't forget to like, because I like that validation. It makes me feel good that I'm helping you out. If you have any questions, be sure to put them in the comments. Don't forget to subscribe. And if you need anything, well, just let me know. Otherwise, we'll talk soon.